Drawing resonance structures in organic chemistry is extremely useful because it helps explain some things that are otherwise a little difficult to understand. I want to make just a few points then that help underscore that. Resonance structures help understand structure stability. That's really important. Which structures are more stable than which? Which structures could be formed because they have enough stability? Help understand reactivity. What could be more important than understanding chemical reactivity? So that's really great. At the same time, it's fair to say that this whole business is a fairy tale. Resonance structures don't exist. They're really fraudulent. It just happens, however, that the thinking behind the whole concept of resonance is a very nice framework for explaining stability and reactivity. And so we continue to use it, even though we know, and you guys must remember, that there isn't a single resonance structure that exists, but rather, when we write resonance structures, taken together, all of them, they are a way of writing what we really have, a hybrid. Real structure is a hybrid of all resonance structures. And I want to point out that you'll notice that when we write resonance structures, p orbitals are always involved. Resonance structures depict the result of overlapping adjacent p orbitals. So you need to keep that in mind as we write resonance structures. What we're really doing is we're talking about the outcome, because we have adjacent p orbitals that overlap. And in some cases, that overlap involves charge. It may be negative, it may be positive. It may not. It may be a radical. Or perhaps it's a stable neutral molecule there where we can just write two different electronic arrangements for the same structure. And so finally, I just said it, and let me write it down. Resonance structures are different electronic arrangements for the exact same arrangement of atoms. Atoms do not move. And there you have it. Here's the essence of writing resonance structures. And let's get to a few examples. Resonance structures help explain what happens when we have a charge next to a pi bond. If we have a positive charge next to that pi bond, we can write a second resonance structure, and I'm going to emphasize that our resonance structure arrows are these double-headed things that do not indicate equilibrium. This is a resonance structure arrow. And we can picture a second resonance structure where the pi bond is here and the positive charge is here. In terms of writing the second resonance structure given the first, we usually track that using arrow pushing, where we picture that pair of pi electrons. This is a pair of pi electrons moving from being shared between these two carbons to being shared between these two carbons. And I want you to notice this central carbon never has a charge, only the end carbons. So in writing resonance structures, charge skips an atom. And I mentioned that there are p orbitals involved, and there must be an overlapping p orbital for every atom involved in the resonance structures. And that is true for here, where we have 3 carbon atoms in this pair of resonance structures, and each one has a p orbital that is involved in writing this resonance structure. Notice that the arrow goes from this line indicating a pair of electrons toward positive charge. Arrows indicate movement of electrons. Electrons are negative, so they move toward positive charge. They move away from negative charge. Let's take a look. This same structure could, the same arrangement of carbon atoms could have a negative charge there. Now you recall, because we've recently talked about it, that negative charge tells us there's a lone pair of electrons on that carbon. So let's write them to remind us. Later we'll get lazy maybe and not write the pair, but simply remember that the negative charge indicates there's a pair there. We could write a second resonance structure where the arrow goes away from negative charge. We picture this pair of electrons being used to form a pi bond, but that can't happen. This carbon will not have enough room in its valence shell because it has a filled outer shell now. That can't happen unless this pair of pi electrons moves up here. So our second resonance structure looks like this. And the allylic system is the same. There are 3 p orbitals lined up adjacent to each other that can overlap, and here they were dissipating, delocalizing positive charge. Here they're delocalizing negative charge. Delocalizing means spread out, right? Positive charge. Here's delocalizing negative charge. This delocalization of charge can happen in other circumstances also. For instance, if you've got a carbon atom with a positive charge, that has a heteroatom attached, let's say nitrogen, has a lone pair of electrons. We can picture that lone pair of electrons being used to form a pi bond between those 2 carbons. And now our resonance structure looks different. This looks odd because we see a positive charge on an electronegative heteroatom. But this resonance happens for a very important reason. It lets all atoms achieve a filled outer shell. And achieving a filled outer shell for all atoms is a very major driving force that dominates other kinds of considerations. So, for instance, this nitrogen is very willing to share this pair of electrons because that creates a resonance structure where all atoms have a filled outer shell. Occasionally, it's helpful to use resonance to explain reactivity, even though the resonance structure themselves don't seem to make the most sense. And I'll show you an example that we'll pull out later because it's a very important aspect of the reactivity of this carbonyl group. Recall that the carbonyl double bond is polarized because oxygen is more electronegative than carbon. One way of showing that is simply to write the partial negative on oxygen and partial positive on carbon, but in the resonance structure convention, this can be shown by picturing a pair of pi electrons moving up to be solely on oxygen. The result is an oxygen atom that has an extra pair of electrons and a negative charge, and a carbon with a positive charge. Now this violates a rule for writing resonance structures that suggests you should not create positive charge when you're writing resonance structures. This does. This suggests to us, and it's absolutely true, that this resonance structure where we create a positive charge is not a strong contributor to the hybrid. It's not. But nevertheless, it is a contributor, and it explains chemical reactivity of the carbonyl group, where things with a negative charge are attracted to carbon and things with a positive charge are attracted to oxygen. So we write the resonance structure because it helps us understand reactivity, even though we realize that this other resonance structure is the major contributor. And finally, there's an interesting case to talk about for resonance that we will talk about in length later, but for the sake of completeness now, so that you aren't totally surprised by us writing the structure later, in ring structures where there are alternating single and double bonds, this is a very special structure. There are two ways to write those alternating single and double bonds that are entirely equivalent. We could say that the double bonds were between these carbons and the single bonds were between the others. And writing one resonance structure from the other is a matter of using, in this case, 3 arrows to show movement of 3 pairs of pi electrons simultaneously. You never have anything else. It's in terms of resonance structures, you have this one or this one. So all these electrons move at once. Now, just to follow the theme of pointing out that these resonance structures involve overlap of p orbitals, it may be worth pointing out that this cyclic system has a p orbital on every carbon atom. So these guys overlap completely in a ring. That this oxygen has a p orbital, as does this carbon. And so these guys overlap completely. And we can picture this carbon and this nitrogen having a simple pi bond with overlap of p orbitals. And in this structure, this would be an empty p orbital, and this one a full one. Notice that in some cases, these writing resonance structures involves lone pairs of electrons donating to create stability by creating an extra charge. In this case, moving a charge from one atom to another, and in this charge, well, moving a charge from one atom to another as well, and creating a pi bond in the process. These resonance structure patterns will be very important to us as we work to explain organic chemistry, the reactivity and stability of molecules. And it's worth taking a good look at them because they'll come up time and again. Take a look at the set of principles here. As you think about making sense of the resonance structure theory of stability and reactivity.